All right, let's start to look at more examples, especially we want to focus on those problems that we need to set up the triple integral by identifying where the domain of integration, where the volume is. And the key here is to make the observation on finding the edge of the boundary. Um, and sometimes we have to do we have to choose which way we want to project, and sometimes we need to use some special trick. Let's go through these examples. Okay, so we want to find the mass uh, of the solid bounded by the surface, those two surfaces. The second one is z equals 19. This is indeed a plane. Okay, the first one is a paraboloid. All right, and we would have to find where this volume really is, and then use the density function to find the mass. So here we want to point out the mass of a solid over a particular region E is determined by the density function integration over this volume. So this is what we need to use. All right, so essentially we need to set up the triple integral, and the question asks us to do this setup only. So where this domain is, where this solid is, we gotta figure it out. First law, x, y, z, and z is relatively easy. Um, z will be a plane. All right, and this we know z equals 0 is the xy plane. Z equals 19 will be a plane parallel to xy plane. All right, and then add the height 19. All right, so we want to know first where this paraboloid. Well, the lowest point of this paraboloid will be the origin for sure, right? Because when x, y both equal 0, z is 0. And when x, y are not 0, z will be positive. So the paraboloid will be opening up. You look at something like this, right? And then there is a plane. The plane will be at the height z equals 19. All right. So there are two things we would have to figure out, I guess. The first thing is what do we where this solid really is? I guess it will be below this plane z equals 19 and above this paraboloid. Okay, so it will be a little bit easier if we project it onto this xy plane, right? So if you do the projection, I would imagine the projection will be a disk like this. And that projection is exactly projected from here. Okay, so now let's look at this domain. So first of all, we want to find where this red curve really is, because that is supposed to be the intersection for this plane and the paraboloid. Okay, this is intersection of the plane z equals 19 and paraboloid z equals x squared plus y squared. So what we need to do is set them together, and then we will see x squared plus y squared equals 19 is what we have. So the boundary of this D in the xy plane is indeed x squared plus y squared equals 19. So this is a circle of a radius square root 19, right? So the D domain is in the xy plane, by the way, is indeed x squared plus y squared less or equal to 19. We can also write it as, because this radius is square root 19, we would imagine x will be bounded by this radius, negative and positive, and y will be bounded by, well, this is circle. We can solve y from this circle equation, which is y equals plus or minus 19 minus x squared, right? So the domain D is given here. I guess it's better to write it in the polar coordinates. So if we write this D in the polar coordinates, obviously theta angle is between 0 and 2 pi, and R is between 0 and the square root of 19. That will be a polar rectangle. So over here, we already determined the domain D, and we would need to write down this solid E by using the D. Okay, where this D? First of all, we need to find a point out of this D, which means we can use the D information. Okay, so y is, so those are the x and the y, and after we choose x and y, then you can imagine you would choose a point, stand there and shoot a laser upwards. And the lower bound for the z will be on this paraboloid, which is x squared plus y squared, and the top bound will be 19. Okay, so with those, we can find the mass by doing this triple integral, right? And the setup of iterated integral will be like this. We choose to integrate along the z direction for the interior integral. The lower bound, as we said, is x squared plus y squared. The upper bound will be 19. All right, and then we treated this as a type 1 region. So we're going to integrate y as the variable for the middle integral, which is from negative square root 19 minus x squared to positive 19 minus x squared. And finally, the variable for the exterior integral will be x. So this is from negative square root of 19 to positive square root of 19. So this is what we do to set up the integral for finding the mass of this solid. Okay, so the procedure is pretty straightforward if you are able to figure out this this domain of the solid. Okay, so it's a little bit tricky if you're not familiar with the quadratic surfaces and intersections. You may need to practice a little bit more. How about we do another problem? Okay, so for this one, we do notice this is in the first octant. That means x, y, z. The first octant means x is bigger than non-negative, y is non-negative, and z is also non-negative. All right. Uh, but here we need to set up the volume integral or triple integral over the solid bounded by this paraboloid in the first octant. Okay, so where this really is, I think we have some idea about it because when x equals 0, y equals 0, we get the highest point of the z. If you notice, that will be 5, I think, here. All right, and how about when z equals 0? That will be an intersection of this paraboloid with xy plane. I think we get x squared plus y squared equals 5. So that will be a circle. Okay, that is a circle. I think this is the region. Okay, and obviously it is only in the first octant, so we need to just check this piece. Okay, so those are the information we need to include. X is bigger than 0, y and z are all bigger than 0. We want to find the volume. That means we need to do this triple integral of constant 1 over this volume E, which is in the shaded region and below this this paraboloid. And if you think of it, the projection of this solid on the xy plane is what? One, two. The projection of this volume E over here will be D, right? That is over here. That is a part of this circle. Remember this, well, as we said, this circle is the intersection of the paraboloid, this, and z equals 0. So we do know it is 0 equals 5 minus x squared minus y squared. So x squared plus y squared equals 5 is this circle over here with x greater than or equal to 0 and y greater or equal to 0. So this is our domain D. Okay, so now think about it. The domain D is, we have x between 0 and, well, this is square root of 5, right? And y is what? Y is between 0 and this circle. We can solve this circle from here, which is y equals square root 5 minus x squared. And we choose the positive square root because y has to be bigger than 0, right? And then this is the domain D. And how about the E? Well, for E, we have x, y coming from D. So this simple means x, y is coming from D. And then we stand in this projection, for example, here, D, and shoot a laser. We know the lower bound for the z variable will be 0. And then the upper bound for the z variable will be on this paraboloid, which is 5 minus x squared minus y squared. So this is our domain. All right, so the volume we're calculating here could be set it up for calculation. And again, we are choosing z as the variable for interior integral. It starts from 0 and stop at 5 minus x squared minus y squared. And then again, we treat this as type y region in the xy plane for this d. So y is between 0 and square root of 5 minus x squared. And finally, we need to set up the limits for the exterior integral, which is for x, which is 0, between square root of 5. Again, as we always remember, the bounds for the exterior integral are always constant. All right. So this is how we set up this volume integral for this one. So now you can see, it still you need to have some idea about the geometric representation. Otherwise, it will have a really hard time to figure out where this solid is and how to set up the boundary for the each integration variable in this iterated integral. Right? Now maybe let's look at another example. And in this one, we want again find the volume solid in the first octant again, and bounded by this plane and this paraboloid. And here it particularly tells us already this plane is on top and this paraboloid is at the bottom. Here it's a little bit tricky. Let's just try to illustrate, because from here we see the paraboloid is opening up. All right. All right. And then there will be a plane. Where the plane is? Well, this plane is sort of coming from here. And we got to make sure again. So we did a similar problem before, but the problem was a bit of simpler than this, because before that we have this plane to be z equals some constant. Obviously here things are a little bit trickier. All right, so we got to figure out what are they for the projection. So this domain D is the projection of this whole volume. And how do we find the projection? Well, things are tricky. We got to figure out though. So first of all, we do know this surface, not the plane, but this lower surface is indeed z equals x squared plus y squared. And at the top is the plane. So I guess we need to find the intersection of this plane and this paraboloid, which is the red curve we drew here, and we project that red curve onto the xy plane, then we can get the sense of what the domain D of the projection of the whole volume really is. All right, so this is the idea. So how about we find the intersections of this plane and the paraboloid? What we can solve? How about we match the z? Okay, so if we do match the z, we see z is x squared plus y squared, which equals 10 minus 2x minus 4y. All right, so let's look at it, what this really is by rearranging this into a standard form. X squared plus 2x, we move this 2x here. We can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also move this 4y here. And then we can also which equals, well, let's save some space, equals 10, right? And here, the reason we save some space for here is obviously we want to complete a square. So if we add a 1 there, then we add a 1 here. Here, I guess we have add a 4. So we add 2 constants on both sides, and then we can complete the square for those 3 terms each. So this is becoming x plus 1 squared plus y plus 2 squared. This is equal to 10 plus 1 plus 4, which is the 15. All right, so this will be a circle, and this circle is the intersection, is the projection intersection of this plane and the paraboloid, which is the edge of the D. So this is the edge of projection D. Okay, and this is quite tricky. If we want to plot it, it'll look like what? So the center of the circle is at -1 and -2, and the radius is the square root of 15, which is bigger than 3, but less than 4. All right, so something like this. 1, 2, 3, 4. Yes, something like this. Okay, so this is the projection of the whole thing is plotted here. So this is a D, right? But there is a restriction. The restriction is we only consider it in the first octant. So this is the part that we need to consider. So that is not the actual D. The real D we are interested in is over here. So how do we find this D region? Well, it's not so difficult after we have this diagram. Okay, we can see what we need to find this point of intersection, which is, so this is the x, this is the y, and this circle is obtained from there. So we just need to find the x value when we set y equals 0, right? So how do we do that? We have x plus 1 squared plus 0 plus 2 squared equals 15, right? So we have x plus 1 squared equals 15 minus 4 is 11. And so x plus 1 equals square root of 11 plus or minus. So x equals -1. It can't not be the negative branch, because if we have minus square root 11, this x will be this one. But that is not what we're looking at. I think we're looking at this one. So this is the x value. This x is -1 plus square root of 11. All right. So for this, we can find the y also by solving y in terms of x. Let's use a different color to illustrate. So how do we represent this edge? Well, we solve y plus 2 squared equals 15 minus x plus 1 squared. So we also see y plus 2 equals square root of 15, well, plus or minus again, right? 15 minus x plus 1 squared, which is y equals -2. Well, we can only choose the plus because this is above the horizontal axis. So this is the y. Okay, so the domain D is what? Now the domain D is clear. We choose x and y. X has to be between 0 and this number, square root 11 minus 1, and y is what? Y is between 0 and this purple curve, which is -2 plus square root 15 minus x plus 1 squared. So this is the domain D. All right. So now with this D determined, the projection for volume determined, it's relatively easy to determine the bounds for the Z variable. Why is that? You think of it. You pick a point, for example, all the way here, and then you shoot a laser up, and then the lower bound will be this Z. Z equals x squared plus y squared, and the upper bound will come from this plane. Remember, for this plane, we have Z equals 10 minus 2x minus 4y. So the triple integral, we need to set up the volume. All right, it will be, again, constant 1. The Z variable is again used for the interior integral. It is between x squared and y squared plus y squared to this one, 10 minus 2x minus 4y. All right, and then we pick the point from this domain D, which is for the y variable, which is integrated in the interior integral. Y is between 0 and the one we just solved over here, -2 plus square root of 15 minus x plus y squared. All right, so the last one will be for x variable, which is between 0 and this. Square root 11 minus 1. So this is how we set it up. So now this one requires quite a bit of the analysis and visualization of this surface and volume. You will need to practice to make sure that you know how to carry out those kind of calculations.